Hello everyone. In this video we present our CVPR 2026 work, Physical Simulator in the Loop Video Generation, or PSIVG. Our method introduces a physical simulator into the video generation process in a training-free manner, enabling videos with more physically consistent and temporally coherent motion. Recent video generation models have made remarkable progress in visual quality. However, they still often struggle to follow fundamental physical principles. Objects may disappear, collide implausibly, float, or move in ways that violate gravity and inertia. In the example shown here, the baseline produces unrealistic behavior, while our method generates motion that is more physically plausible. This motivates our work on improving physical consistency in generated videos. Our key idea is simple. Instead of asking a video generator to invent physically correct motion on its own, we insert a physical simulator into the loop. The simulator provides trajectories that better reflect the dynamics of the scene, including the motion, speed, and rotation of objects. And these trajectories are then used to guide video generation. In this way, we combine the visual strength of diffusion models with the reliability of physics-based simulation. Here's an overview of PSIVG. Our pipeline has 4 stages: template generation, 4D perception, physical simulation and rendering, and final video generation with test time optimization. First, given an input prompt, we generate a template video using a pre-trained video generation model. This template provides an approximate scene layout, camera motion, and initial object movement, but it is not guaranteed to be physically correct. We use it as a starting point for further perception and simulation. Next, we process the template video with a 4D perception pipeline. From the video, we reconstruct the scene, estimate the foreground object geometry, recover camera poses and object positions, and estimate the initial object dynamics. This stage gives us the information needed to initialize the physical simulator. Then, we estimate physical properties and use the material point method to simulate a physically plausible trajectory over time. From the simulated motion, we render guidance signals, including point correspondences, dynamic foreground masks, RGB renders, and optical flow. In the final generation stage, these rendered signals are injected into the video diffusion process to produce videos that better follow real-world physics. In addition, to improve the consistency of object appearance during motion, we introduce a test time optimization step called TTCO. The idea of TTCO is to use simulator-derived pixel correspondences to preserve the appearance of the object across frames. This provides an additional signal that helps maintain texture consistency, especially under large movements and rotations. For the learnable parameters, we chose to optimize modulations to text tokens and features in intermediate layers of the diffusion model, as we find that this helps the texture optimization to be more localized in targeting the foreground objects, while preserving the quality of the background. Compared with existing video generation methods, PSIVG also performs well quantitatively. In particular, it achieves the strongest motion controllability metrics, showing that the motion in our videos is much closer to the simulator-guided trajectories, while remaining competitive on general video quality metrics. Next, we compare qualitative results in several static camera scenes. Our results are shown in the bottom right of each set. Compared with existing baselines, our method produces motion that is more coherent and more consistent with the expected physics of the scene. Here are more static camera examples. Again, PSIVG better preserves object identity while following a physically plausible path. Moving camera scenes are even more challenging because the model must preserve object motion, background consistency, and camera motion at the same time. In these examples, our method remains more robust than the baselines, producing videos where the object motion stays physically meaningful even as the viewpoint changes. These additional moving camera examples show the same trend. We also conducted a user study comparing PSIVG against the 5 strongest baselines. The results show a strong preference for our method, with over 80% preference overall. Next, we ablate the effect of TTCO. Both the quantitative results and the examples below show that TTCO helps preserve texture and appearance as the object moves. This slide compares our prompt-based optimization design with a LoRa-based alternative. We observe that the prompt-based design produces more stable and coherent results, while introducing fewer artifacts in the background. Finally, we show an example involving a more complex material, a water sphere dropping onto a muddy floor. This example illustrates the broader potential of physics simulator in the loop generation. Although highly complex materials remain challenging, this result suggests that the framework can extend beyond rigid objects toward richer physical behaviors. To conclude, we presented PSIVG, a framework that improves video generation by integrating a physical simulator into the generation loop. Our method generates videos that are more physically consistent while maintaining strong visual quality. For more information, please visit our project page or GitHub page. Thank you for watching.